Hi, this is Keely, and we're going to look at a fluid problem where the pipe actually goes up and narrows and see how that's handled. I did a previous video where the pipe just narrows and we figure out the pressure and the velocity, but this one we have the pipe being elevated. Now normally there's a ground level down here and they tell you the height between the ground level and the center of the pipe on either side. But since Bernoulli is based on energy, we can reset our zero to whatever we want. So I always set the center of the lowest part of the pipe to be my 0 point, and then I have a positive height that it goes to. So this will become my H2, while H1 is going to be 0. So that's one thing I do to help simplify the problem. So let's see what we've got here. So we've got seawater, density 1,025 kilogram meters cubed, has a speed of 3 meters per second in the lower pipe that's closed. So we're talking about gauge pressures here, not absolute pressures. Levels off at a height of 4.2 meters, and the radius goes down to 4.5 centimeters where it was 6 centimeters. And we need to determine the flow rate of the water and the pressure and velocity at the elevated position. All right, so flow rate. So flow rate is simply area times the speed of the fluid. So for this is a circle, so the area is pi r squared, and we've got the velocity. So at this lower point that we know all those numbers at, well, we first need to make sure we change that centimeters to meters. So it's 0.06 meters. So pi times 0.0606 meters squared times the velocity, which is 3. All right. So I'm just going to use 3.14 for pi. So 3.14 times 0.06 squared times 3 gives me a flow rate of 0.034 meters cubed per second. So that's the volume of water that flows through that pipe every second. Now we need to figure out the speed of the water as it goes up through this smaller section of pipe. So we're going to use what's called the continuity equation. The continuity equation is basically the flow rate here has to equal the flow rate here, because all the water coming in has to go out as things move. And so as the pipe narrows, that volume still has to be the same. So to get that volume out, it must travel faster in a narrower pipe. So for that we need pi r squared times velocity equals pi r squared times the velocity at the second part. Okay, basically it's area times velocity equals area times velocity at the respective positions. So at points 1 and 2. So this would be my point 1, that would be my point 2. All right, now here's the neat thing. If you start solving it algebraically like I did, something nice happens. The pi's cancel out, so you don't have to fool with them. And so we have 0.06 squared times the speed of the water in that lower section equals, now on the upper section, it's next down to 4.5 centimeters, so that's 0.045 meters, 0.045 squared times our speed in the lower section. So let's see what we get. So 0.06 squared times 3 divided by 0.045 squared equals our speed in that upper section is going to be 5.33 meters per second. Okay, so we've got the speed of the velocity in the upper part, and we got the flow rate. Now we need to figure out the pressure. And for that, we need Bernoulli. And so Bernoulli is pressure at one point plus rho GH at that point plus 1/2 rho V squared at that point equals the pressure in the new section plus rho GH in that new section plus 1/2 rho V squared in that new section. All right, so what can we get rid of? Well, since I reset my 0 point, we're going to say that height is 0, and this is 4.2 meters up. So this term goes away. And that's basically it. We can't simplify this one anymore. This one's not nice. So what we can do is actually start plugging things in. So the pressure in the lower section is 80,000 plus 1/2. The density is 1,025, and the velocity at the bottom section was 3 squared equals the new pressure that we got to find plus 1,025. Gravity, I'm going to use 9.8, and the height was 4.2 meters plus 1/2 1,025 times our new velocity, which is 5.33 squared. Let me slide this over a little bit. There we go. All right, now it's plug and chug time. Get out your trusty calculator and start typing things in. So we got 80,000 plus 0.5 times 1,025 times 3 squared, which is 9, equals, on this side, we have 84612.5 equals our pressure plus whatever this turns out to be. So 1,025 times 9.8 times 4.2 plus half of 1,025 times 5.33 squared equals 56748.56, kind of rounded off. And so now we just need to move that over so we can find the pressure at point 2 at the top of the heel. So 84612.5 minus 56748.56 gives us a pressure of 27,863.94 pascals. Or now Pascal is the same thing as Newton per meter squared. Our pressure dropped down. So let's take a look at this. So it elevated, so that should drop the pressure even if the pipe stayed the same diameter. But since the pipe got neck down, it got narrower. That also meant the fluid's traveling faster, and a faster flow of fluid means less pressure as well. So it makes sense that our pressure at this elevated position is less than the pressure we started off with, 80,000. Okay, so what happens if the water is falling downhill in a closed pipe instead of uphill? So let's see what one of those looks like. So here's a situation where we have the density of water, and this is plain water. It's flowing at 2.5 meters per second at the top of this incline. The radius of the pipe is 5 centimeters at the top. Radius next down to 4 centimeters at the bottom. And it drops a height of 3 meters. And we've got to figure out the pressure and speed in the lower section this time. All right, well, we got a couple things we need to do. First of all, if you look up here, density water is given in grams per cubic centimeter. That's not the unit that we want to match pascals and other things. We need to change that to kilograms meters per meter cubed. So we're going to have to do some conversion. So how are we going to do that? Well, here we go. 1 gram per cubic centimeter. And we want to eventually get to kilograms per cubic meter. So there's 1,000 grams in 1 kilogram. And there's 100 centimeters in 1 meter. But this is cubed. And so we need a total of 3 of those in order to completely cancel out that unit. So these 3 cancel out the cube at the bottom, and these grams cancel out those, and just leave us with kilograms per meter cubed. And that ends up being 1,000 kilograms per meter cubed is the density of water in those units. So we just have to convert. The easy way is just multiply by 1,000. I'll do a video later of converting from all the different representations of density over into this. But right now, a shortcut is just simply multiply by 1,000 if you're going from this to kilogram per meter cubed. Let's figure out the flow rate. So flow rate is area times the speed of the fluid. So in the upper section here, where we know all the numbers, we know that 5 centimeters is really 0.05 meters. So we have pi r squared times the speed. So that's 3.14, which I'm going to use for pi. The radius is 0.05, but that's squared, and the velocity is 2.5 meters per second. So 3.14 times 0.05 squared times 2.5 gives me a flow rate of 0.0, let's round it off to 2 cubic meters per second. To find the speed at the lower end, we're going to use the continuity equation. Continuity equation is area times speed equals area times speed from one location to another location. And so we can do a neat thing. Well, since we know the flow rate at this section right here, we already know that that's 0.02. Now, I'd used a different method in the previous problem that let us cancel out the pi's, but since we know the flow rate, let's just use that for this one. So we know area is pi r squared times our new speed, so 0.02, pi 3.14, our new radius, and next down to 4 centimeters, so that's the same thing as 0.04 meter, 0.04, and we find our new speed. Don't forget to square that. Easy mistake to make. So 0.02 divided by 3.14 divided by 0.04 squared gives me a flow rate of just under 4. So we're going to say velocity at 2 is 3.98 meters per second. Or actually gives me the velocity there. So now, to finish things off, we need to figure out the pressure. So, back to Bernoulli. P1 plus rho GH1 plus 1/2 rho V1 squared equals the pressure in the second section plus rho G height of the second section plus 1/2 rho V squared of the second section. All right, so what can we do? Well, we could set this as being 0 and the height went down 3 meters. I don't like really using negative numbers, so I'm going to still set this as my height is equal to 0. And so this height will be, actually H1, be 3 meters. So that means this term falls out. because the height at 2 I defined as being 0. And so the top of the pipe is at 3 meters above the ground, or above this section, I should say. Again, we're measuring from the middle of the pipe to the middle of the pipe. You always do that. And so now we can plug numbers in and see what we get. So we've got the pressure at the top is 1.2 times 10 to the 5th pascals, plus the density, which is 1,000, times 9.8 for gravity, and the height is 3 meters, plus 1/2, density is 1,000, velocity at the top is 2.5, and that's squared, equals the pressure at the bottom, which we don't know, plus 1/2 of 1,000 times the velocity at the bottom, which is 3.98 squared. And again, now it's time for the calculator. So let's go ahead and calculate all of this. So 1.2 times 10 to the 5th plus 1,000 times 9.8 times 3 plus 0.5 times 1,000 times 2.5 squared equals, that whole mess becomes 1,52525 equals, let's go ahead and calculate this. So that's 500 times 3.98 squared. And so that becomes, let's see, P2 plus 7920.2. And then we just move that over and subtract. So that gives me a pressure of 1.4, let's call it 5 because it's going to round up from my answer that I got here, times 10 to the 5th pascals. And so the pressure actually increased when that water went down. Even though the water is moving slightly faster, it went from 2.5 to nearly 4, so that should reduce the pressure. But it also dropped 3 meters, so you've got technically more like the weight of that water pressing down, and so our pressure actually went up slightly. All right. Thanks for watching, and please tune in for some more physics and like and subscribe to the channel. Thank you. Goodbye.